All right, for the last video here, we're going to just go through hypothesis testing in 4 steps. So what we have here is step 1, hypothesize, 2, prepare, 3, compute to compare, and 4, interpret. So we're just more or less revisit the steps we did in the previous and come to a conclusion. So hypothesize, we want to state your hypotheses about the population parameter. Prepare, we want to get ready to test. State your significance level and choose a test statistic appropriate for the hypotheses. Okay, so we want to state and check conditions required for future computations and state any assumptions that have been made. So this is a real important part. We need to make sure that our data is not biased, and we need to make sure that our central limit theorem approximation is valid. Right? So those are the things that we really need to verify before we go on to steps 3 and 4. So step 3 here is we want to compute to compare. So we compute the observed value of the test statistic and compare it to what the null hypothesis said you would get. Okay, so we want to find the p-value in order to measure your level of surprise. Okay, 4, we want to interpret, do you reject or not reject the null hypothesis? So really, with hypothesis testing, you have to make a decision. Either we reject the null or we do not. Okay, so, and then whatever decision you make, you need to interpret it within the context of the data. So that's what we're going to do today. In step 2, as far as the assumptions required for the proportion, right, and dealing with the proportion, it's the same assumptions that we used for central limit theorem, essentially, meaning that, our data has to come from a random sample. The outcome of each observation, they're independent from each other. 2, we need to have a large enough sample in order to use the central limit theorem, okay, to use the normal distribution. So one thing to note, the difference here between confidence intervals and hypothesis testing is that for confidence intervals, we're using sample proportion, okay, but for hypothesis testing, we're using the population proportion under the null hypothesis, okay? So we need to make sure that both of these are at least 10, because remember what these assumptions are checking in approximation is to make sure that the distribution is not skewed, right? We want to make sure, 1, that we have a large enough sample size, and 2, we need to make sure that our distribution is not skewed to the right, in this case, if this is not true, or skewed to the left, in this case, if it's not true. So as long as these products here are both greater than 10, then what we're saying is that the distribution is definitely unimodal symmetric, and you have enough data for a valid approximation. And then of course here, big populations, right? Our populations need to be at least 10 times larger than the sample size, okay, especially in sampling without replacement. So as far as compute to compare, we're going to compute what we call a test statistic, which we saw before, or we call it Z observed. Right, so really this is the difference between our real world and the null hypothesis world, and we compare this difference in terms of standard error, right? So this is really the expected difference we should see between a sample proportion and the null hypothesis proportion, right? So here, as far as calculating the p-value, this is just a p-value guide. If it's two-sided, this is how we calculate the p-value. If it's one-sided, this is how we calculate the p-value. If it's one side, that's how we calculate the p-value there. Okay, so so if it's less than, remember p-value, probability of observing our test statistic and more extreme values, right? So the direction of extreme is determined by the alternative. Okay, so this is less than, therefore this is less than or equal to. This is greater than, therefore this is greater than or equal to. And this quantity here, this is just, really, if it's not equal to, then it just means that we just suspect that there's a difference. So it could be a lot larger than P naught or a lot smaller than P naught. But really, we're just interested in the absolute distance from this value here. So that's why we have the absolute value here and here. Okay, but so let's see an example here. So based on a recent study, roughly 80% of college students in the US own a cell phone. Okay, do the data provide evidence that the proportion of students who own a cell phone in this university is lower than the national figure? Okay, use a significance level of 5% or alpha 0.05. Okay, so from here, can you determine the null and alternative hypotheses? Right, so of course our research question is the alternative hypothesis here, HA. And so here we're saying the proportion of college students that own a cell phone has decreased from 80%, right? Because they're saying lower than the national figure, right? Whereas the null hypothesis is skeptical of our claim and is saying, well, the proportion of college students that own a cell phone is 80%, right? So in terms of statistical language, we have null hypothesis, population proportion is 80%, versus the alternative hypothesis that population proportion is less than 80%. Okay. So before we move forward, we have our null hypothesis and our alternative hypothesis, and we have our significance level. Now, we don't go straight to the test statistic. We need to verify our assumptions or argue that they are good. So first one is random sample. So here, the data does come from a random sample. Okay, in this study, they actually did go and randomly select college students to participate in their study, meaning, they probably listed their student ID numbers and randomly selected ID numbers and found the students to participate. 2, large sample. So the sample size here was 310, right? So we do the product of 310 and the proportion under the null hypothesis, which is 80%. And then we do the sample size 310 times 1 minus the proportion, which would give us 20%. Okay, so this is a proportion of students that don't have a cell phone. So if you do these products, 310 times 0.8, 310 times 0.2, these will both be greater than or equal to 10. Okay. So, and large population. So we're just saying, of course, we're sampling these students without replacement. So we're just saying, is it safe to assume that the population of college students is at least 10 times larger than the sample size of 310? So 10 times larger is just add a 0, right? Multiply it by 10. So is it safe to assume that the population size, right, is at least 3,100? And I'm going to say this is a larger college. So yes, it's definitely safe to assume that. Okay, and of course, independence, right? Our responses of college students, the responses of college students are independent of each other. So hopefully due to this random sampling, we're just asking students one at a time, right, individually. So their responses are independent, okay? So what I do here is I go into StatCrunch, and what I do is for all the responses from the students, I have it count the number of yeses out of the total number of responses, okay? So, and in StatCrunch, I'm able to give it the null and alternative hypotheses, and what it will do is conduct a test for me in the test. So what I have it do is go to the variable cell and then go down that column and count all the yeses, okay? And the number of yeses out of the total number of responses, right, that's our sample proportion of students that own a cell phone. So yes means they own a cell phone, no means they don't. Okay, and so here the count, that means 243 students said yes, they had a cell phone out of the total number, which is 310 in our sample. So if we do 243 divided by 310, you get your sample proportion, which is 0.7838. So this 78.38 is definitely less than 0.8, right? This is like 78.38%. That's definitely less than 80%, but it's significant, right? So what we need to do is compare, right? We take the difference of 0.7838, the sample proportion, and the null hypothesis proportion, right? And we say, well, it's roughly maybe a little less than 2%, and want to know if this is significant or not. So the standard error here, this is saying the typical distance between the sample proportion and the null hypothesis proportion of 0.8 should be about 2%, right? It should be within 2%, right? If we're doing 68% rule, right? 68% of sample proportion should be around 2% plus or minus, right? So if you look here at 0.78, I mean, that's within 2% of 80%. Right, so here if I calculate my test statistics, so that's the standard error, assuming the null hypothesis is true. And then of course my z-test statistic here is, well, this is saying this is negative 0.7, if we round here, this is negative 0.7, my sample proportion of 0.7838 is negative 7 or is 0.7 standard deviations below the null hypothesis proportion. Right, And the probability, assuming that the null hypothesis is true, assuming that the true proportion is 80%, the probability of observing my sample proportion of 0.7838 and smaller values, right, because this is less than, so smaller values, is roughly 0.2389. Okay. So in StatCrunch, I can actually visualize this, and this is what the p-value looks like. All right, this is negative 0.71 and smaller values. So this area here represents the p-value. So remember, this is a standard normal distribution, right? So it goes from -3 to 3 roughly. Okay, so we're using the central limit theorem here to approximate this probability. Okay, but this it gives you a visual of this p-value here. Okay, and this is the field I plugged in to find the sample proportion, but I'll give you an example. But I'm just looking at variable cell, count the yeses, and then here I'm telling you what the null and alternative hypotheses are. Okay, but I'll show you an example right now. Okay, so anyways, so now that we've crunched the numbers, right, now we can interpret our result here, right? So here, now whenever you get the p-value, you always compare it to your significance level. And if p-value is smaller than this, then we reject the null. If it is larger, then we fail to reject the null. So in this case, our p-value is greater than alpha. That is 0.2389 is larger than 0.05. So we failed to reject the null hypothesis. So what this is saying is that there's roughly, assuming that 80% is the true proportion, the probability of observing our data, right, it's roughly a 23% chance, right, 24% chance. So it's pretty likely that we observe the sample proportion, given that the true proportion is 80%, right? Because remember, these sample proportions are centered around the true proportion. So now we made our decision. Okay, our decision is to fail to reject the null hypothesis. Okay, so when we interpret this result, we always state our significance level first. We say at a 5% significance level, there is not enough evidence to conclude that the proportion of cell phones owned by college students has decreased from 80%. Okay, so pretty much we can't say that it's decreased, so therefore we're just saying, yeah, more or less we can conclude that it's right there. It's right there at 80%. Okay, it's still nothing has changed. Okay, and just as a brief thing is, you always have to relate your output to the quantities here. So I'm just providing some help here. So this sample proportion is the p-hat, right? This total is the sample size 310. 0.80 is p-naught, right? Standard error, right, is the square root of p-naught 1 minus p-naught over n. So remember, we're plugging in the null hypothesis value here and 1 minus the null hypothesis here. Because notice, remember, standard error for confidence intervals, we had p-hat, right? We would have plugged in 0.7839 here, 1 minus 0.7839 for confidence intervals. Because remember, confidence intervals are purely data driven. Whereas hypothesis testing, they're always centered around the null hypothesis claim. Okay, so that's how they get this number here. Okay, that's how they get this number here. And then of course, our z observed is this z stat here. Okay, so how they did that was sample proportion minus proportion under the null all over that. So I mean, we can write it out here. I could write insert, let's see, equation. Oops, I could do equation here. I'm gonna do a fraction here. So I could say this was roughly 0.7839 minus 0.80, that's p naught, and then standard error, assuming the null hypothesis is true, so 0.0227. Okay, so that quantity there is equal to roughly that number. So I just rounded here this z stat, so I rounded at the 4th decimal, so you get 0.001. Okay, it rounds down there. And our p-value is, that's how we found the p-value, and that's what it's equal to right there. Okay, but let me show you real quickly in StatCrunch how I did this test here. Right, so here I'm in the cell phones, I'm looking at the variable cell, and here I have a bunch of yeses and nos. Right, so I want to construct a hypothesis test on the proportion of yeses in this column of data here. Right, so here I could go to stat. I go to stat and I go to proportion stats and I do one sample with data. Okay, so what I do here is is, well, what variable are you interested in testing? Well, it's cell. Okay, this is the cell variable, so the cell shows here, and success here is yes. So make sure that you type it in exactly the way that it's here. Okay, so it's all lowercase letters. If I had plugged in yes with the capital Y, it's going to give you 0 successes. Okay, because for computers, lowercase y and uppercase Y are completely different things. Okay, when you're doing text mining, you're having a computer look through letters. You need to be very clear as far as what you wanted to search for. So here we have to put lowercase. Okay, and then of course here we had on the null hypothesis it was 8.8, and then of course we're doing one tail test, which is less than, and then here I'm going to click this for the p-value plot. Okay, so I'm looking at the variable cell, counting the yeses out of all of them, right? And then I'm constructing the test, all right? And so that's what we get here. Okay, that's what we get here. So that's the same result that we got previously with the other data. And by clicking that p-value plot, if you hit this arrow down here, that's where we get the plot. So you can visualize the area underneath the curve for the p-value, right? So remember, p-value is all in terms of z, so it's standard normal. Okay, standard normal. Okay, all right. And just before we head out, I want to show another example here involving the shark data. So remember, in the shark data, the surfer, when we're looking at confidence intervals, the surfer walks in and says, 50% of attacks occur in the US, and our confidence interval did not agree with that, because every value in our confidence interval was in the 30% range. So obviously we rejected the surfer's claim using the confidence interval. But I could do a hypothesis test here if I wanted to. So country, right? This is the location. It's in the USA or Australia, USA, Australia, Egypt. So there's all these different locations here that were recorded. So here what I want to do is run a test. So I want to go to proportion stats, one sample with data. Okay. And what I want to do here is I'm going to look in that country, okay, within country, and my success here is going to be USA. USA. So make sure it's typed exact same way that is typed here. So all uppercase. So here, I mean, the claim made by the surfer is that it's 50% of the attacks occur in the US. And so my alternative here is I really had no idea whether it'd be less than or greater than. I'm not that familiar with surfing and shark attacks. So my research hypothesis, I suspect that is not true. So it's just not equal to. Okay, so this is a two-sided test. Okay, so here I'm going to have it give me my p-value plot. So if I compute that, okay, I get my results here. Okay, so my results here saying that, so here it's saying successes are USA. This is my null hypothesis, my alternative. So it's saying there were 2,082 attacks in the US out of a total of 5,893 attacks recorded in the data. And here the sample proportion is 0.353. So it's definitely smaller than 0.5, but is it significant? So we look at this difference compared to the expected difference we should see for this here. So this here is roughly, this is the expected difference we should expect to see between the mean, between the proportion on the null hypothesis and the sample proportion, which is roughly a 0.6%. Okay, and the difference we observed here is roughly like 15%. Right, so when you compute your test statistic, it's saying that your sample proportion is 22 standard deviations below the null hypothesis proportion. So this is what it means is very far away from the null hypothesis reality. Okay, the reality from the real world is way smaller than the reality of the null hypothesis. Right, so in this case, our p-value, it just gave up. It's saying it's so small that it's less than 0.0001. Okay, and actually if we look at the visual here, this is what we get, right? So this is the standard normal distribution, right? So we're just looking at a distance from here that is 22 or more. Doesn't matter in direction. So here's negative 22 and smaller, positive 22 and larger, right? We're just doing absolute distance away from the center, and really there's no area underneath the curve to calculate, right? So this probability is pretty much 0. right? So this is a surprise, right? This is a surprise, right? What this is saying is that it's pretty much impossible that we observe the sample proportion given that the null hypothesis is true, right? So the p-value, the probability of observing our data, 0.353, given that the true proportion is 0.5, is pretty much impossible. That is a surprise. That is a surprise there. So therefore, based off this hypothesis test, we would conclude at a 5% significance level, there's enough evidence to reject the surfer's claim of 50%, and therefore we would conclude that definitely the proportion of attacks in the US is not 50%. Okay, so because it's not equal to, that's all we could say. Okay, if it were less than, we could say it's less than 50%. If it were greater than, we say greater than 50%. But since it's not equal to, all we could say is that it's not equal to 50%. Okay, all right, but I just want to show you that example in StatCrunch really quickly, and we'll have some more examples later.